So, we have found out an expression for overvoltage when you have a preferential charge transfer. For example, if charge transfer is taking the equilibrium reaction towards the more and more ion formation reaction, then it would be I A. For example, if this is my reaction M, this reaction is preferentially happening. So, that time I will consider I C, and if this reaction is preferentially happening, I will consider this is as I A. Now, that time we see that we have a preferential, if this side is going, the backward reaction is happening. So, preferential ion formation is taking place. So, preferentially you are taking out electron from metal atom. Now, that time we have found out expression for overvoltage, because when you have non-equilibrium for the formation of metal ion or formation of metal, that time we can find out what is overvoltage, or the we can quantify the polarization. We have found out the expression, which is this is my general expression, where I initially started with the total polarization, and then finally if it is anodic side, then we have put it I A, and this is neta A, and this is beta A, which is the Tafel slope. And then we can also write it in the form of beta A log I A plus some constant. So, this is my Tafel equation. This is my Tafel equation. Similarly, I could find out what is the Tafel equation for cathodic reaction. So, that case neta C would be beta C, which is the Tafel slope cathodic process, log I C plus C dash, which is also a constant. And now, in this case beta A is RT alpha NF into 2.303, we have seen that, and beta C is basically 2.303 RT 1 minus alpha NF, and where alpha is the symmetry factor, and generally we take it as 0.5. So, the distribution of energy states or energy level of the ionic spaces as well as the atomic spaces will vary as per this alpha, and this alpha, if it is 0.5, that there would be equal distribution or equal change in the anodic side as well as cathodic side. And we consider this is to be a negative value, just to have a sense that cathodic polarization is going towards the negative side. That means potential drops from the equilibrium potential, and this is considered to be positive. Anodic polarization means the increase in potential from the equilibrium value. Now, we have also seen that if you would like to see what is my overvoltage as a function of log I, now when the overvoltage is 0, that time I know if the overvoltage is 0, that time I A equal to minus I C equal to I 0. So, when this condition is satisfied or equal to 0, that time we know that there would be no net current flow in the system. Because I know what is my net current flow, I know that I net, or the measured current what you are seeing in the circuit, that would be I measured would be equal to I A minus I C. I am taking mod. just to indicate the value. Now, if you see that IC is more, this should be along the direction of IC, and if IA is more, then IA is more than IC, then this direction, the measured current direction would be along the IA. So, that case this would be 0. So, I won't have any net current in the system. So, I have this point, let us say this is my point, which is corresponding to some I, that I would be I0. And now, if we would like to see the cathodic polarization or anodic polarization, I need to find out what would be my IA and what would be my IC. Let us say I know what is my IA with the progress of polarization along the positive side. This is positive, this is negative side. So, that will be governed by this equation. So, this is my anodic polarization line. Since this is plotting with respect to polarization as a function of log I. Now, similarly, I can also find out what would be my cathodic polarization if I know IC. Okay. Accordingly, I will also find out IC. This is my cathodic polarization line. So, now I have both the lines, and here you see has a negative slope. That means, because we have already considered that the slope for this cathodic polarization is negative, and that is beta C, and in this case it would be beta A, which is positive. Now, the point is, initially we have considered that we have started with total polarization beta log I by I0. Now, out of that total polarization, alpha fraction would be anodic polarization, and 1 minus alpha fraction would be cathodic polarization. Now, here we have shifted it from neta to neta A and neta C. Now, we have to see whether this change from this is going to have any difference or not. If we see that there is no difference, then we can easily put that. If we see that there is difference, then we should not convert this directly from this. We have to have some logic that why we are writing neta A and neta C from the total polarization. Now, let us have a bigger graph. This is my log I, this is my polarization. Now, condition 1 we have already seen, this is my condition 1, where overvoltage is 0. Overvoltage 0 means polarization is 0, and polarization 0 means IA equal to IC equal to I0. So, I can pinpoint that point. Let me see that this point is this. So, correspondingly I have this value, this is I0. Corresponding value would be I0, and corresponding polarization would be 0. Now, as 0 means, this means 0 polarization means neta equal to 0 means E minus E0. In this case, let us say if we consider that the equilibrium potential is reversible non-corroding potential or the standard reduction potential, that time it is basically 0. So, we do not have any current flow because IA equal to minus IC. So, I measured is basically 0. Now, let me take some reasonable value. Let us say beta A, let me take it as 100 millivolt per decade of current density. Since I have log I on the x axis, so millivolt, and beta C is equal to minus 100 millivolt per decade of current density. Now, let me consider for a particular reaction, that case in case of mono M plus plus E, for this reaction let me consider I0 is 10 to the power minus 2 ampere per centimeter square. Now, in this case, if I take the potential to the positive side, that means I increase the anodic current. So, this is my anodic current IA, this is my IC. So, I increase my anodic current. So, if I increase my anodic current, let us say at some position I have the over voltage to be 100 millivolt, plus 100 millivolt. So, if it is plus 100 millivolt, let me find out what would be the amount of IA. So, this would be equal to beta A log IA by I0. So, from this I would see that IA is coming out to be 0.1 milliampere per centimeter square. Similarly, since I know that I have already gone to a positive side, which is 100 millivolt, let us say this is my 100 millivolt, this is my 100 millivolt. So, I know that I have already reached there. So, I can calculate what is my anodic polarization, fine. So, I can find out where is my point, this point, let us say this is my point, this is my point. So, like that I can also find out what would be my cathodic current, because so then I can draw this cathodic anodic polarization line, this equation, it will be governed by this equation. So, I can have a line for anodic polarization. Now, similarly, when I see that IA has increased compared to IC, that does not mean that reverse reaction is not happening. Reverse reaction is also happening, but at a much slower rate. So, IA, if I know IA, similarly I can also find out what is IC, because similarly I can have an imaginary line for cathodic polarization. So, my cathodic polarization line cutting the 100 millivolt at this point. So, I also can be, this is my IA and then this should be my IC. So, I can also find out IC, just I would put in this equation I will put 100 millivolt, which is plus, and I know what is beta C is minus, and accordingly I can find out IC. So, the IC will see that, so I can put NC equal to 100, since I know what is my over voltage. So, would be equal to 100 millivolt equal to minus 100 millivolt per decade of current density, because I have to put beta C is negative. So, minus log of IC by I0, and from that I can find out IC is coming out to be 0.001 ampere per centimeter square. Now, if you compare these two current, this is one current, this is another current. So, current density is rather not comparison of current, rather current density. The current density, if you see, the anodic process is very, very large, and if current density for the anodic process is very, very large, that means that the cathodic process is very, very slow. And now, if I would like to find out what would be my measured current would be then I measured. So, I know these two values. So, I measured would be equal to IA minus IC. So, it would be equal to 0.001 1 minus 0.001. Now this is equal to 0.099 ampere per centimeter square is almost equal to 0.1. Now you see that I measured equal to IA. So a very important conclusion we have reached, I measured equal to IA if the overvoltage is very large. At that case, or on the other side, if the current density for the anodic process is very large compared to the current density for cathodic process. So that means if the polarization effect due to cathodic current, when we have reached to a very high positive potential with respect to the equilibrium potential, is going to be negligible. So neta C, so let me write it on this side, neta C would be negligible if overvoltage anodic voltage is very large or IA IC. So that means the total polarization is going to be the effect of only the anodic current. So that's why from this we can easily write this. Since the total polarization is only the effect of this, in other way around, if you see this, if we consider what would be the effect of the cathodic current on the polarization, since cathodic current always would lead to cathodic polarization, or the potential should drop towards the negative value, here you see it is going to the positive side. Again, from the sign convention, it does not lead to any, does not satisfy my polarization effect. So that means I can easily write this because of this. So now from this I can easily write this for cathodic polarization. I can write for cathodic polarization, anodic polarization. I can also write for cathodic polarization. I can also, this slash means you just replace A with C in case of cathodic polarization. So now coming back to this curve, so now I can pinpoint what is my cathodic polarization line, what is my anodic polarization line. So this is my cathodic polarization line, this is my anodic polarization line. So I can write those equation. This is my neta A equal to beta A log IA by I0, and this is equal to C equal to beta C log IC by I0. Fine, no problem. But the point is, I cannot measure IA or IC individually. Rather, I always measure what is my measured current from the circuit. So I need to see what is my measured current. Now from this you can easily understand that I measured equal to IA at a very high over potential. Now let us say at this, now when the overpotential is 100 millivolt, that time I see that I measured equal to IA. So what would be my corresponding point there? My corresponding point would be close to this, close to this. Similarly, I drop down to little more lower over voltage. I will see this, my I measured point would shift to this. It would be very close to IA. Similarly, if I drop down further, I will see that my current value is coming out to be this. This is my I measured. I am just plotting I measured. Gradually, I can see that I measured will come here. Now, as I come close to this, so I will see that I measured would have the effect of IC also. At a very, very high positive over potential, I measured would be equal to IA. As you go down, because as you go down, that means if you have a lower and lower anodic overvoltage or anodic polarization, you see that IC effect is coming, because that time I measured cannot be equal to IA, rather I measured would be equal to IA minus IC. So, this point will shift. Fine. So, now I can connect this all those locus, all those points. So, now I can, let me connect all those points. I have connected all those points at different overvoltageal value. So, at different overpotential values, I have just found out what is my I measure, and this is the plot of my I measure. And I measured it, actually we measure from the external, from the circuit. We do not measure IA or IC separately. Similarly, the other side also we can have similar plot. So, this is my I measured is nothing but IC minus IA, and this side is I measured equal to IA minus IC. Sorry, this line. This line. So, now what curve we will see, what experiment data we will see when we do polarization, that means we forcefully take the potential towards the positive side or the negative side, that we can easily do by supplying positive current or negative current into this. So, that time I can have a cathodic current and we can forcefully take out electron from metal, we can have anodic current. So, that time I will have a plot like this, and from this it is very clear what is my I0. And the important issue is you see at a very, very high over voltage, this experimental line is merging with the straight line part, because at a very, very high over voltage line, over potential line, experimental line is basically this line is experimental data, and this is my actual anodic cathodic current, and this is my anodic current and corresponding over voltage. So, if you would like to find out what is my I0 for this reaction, I will have this curve and we have to find out what is my straight line region, and the straight line linear region, from the linear region I will draw a tangent, and also from the linear region I will draw a straight line, and I would like to see where it cuts along 0 over voltage. That is my point for I0 for the particular equilibrium reaction or reversible reaction. So, this is my experimental plot. So, let me find out, let me put the experimental line as a solid line and other line as dotted line, which are not experimentally found out. So, my dotted line would be this is not my experimental plot, this is inherent in the system, this is inherent in the system. So, I have gotten a polarization curve. So, let me remove all the dotted lines and then I will only see the polarization curve. This is my polarization plot, and that plot you actually see experimentally. So, I can find out what is my polarization curve, that means over voltage versus log I. Now, we can also convert it into absolute potential. What we have to do? At positive voltage, this is corresponding to E0. 0 corresponds to E0 when we convert it into absolute potential. This is my over voltage data. Let me see another axis where I would like to see what is my absolute potential. Let us say you have measured the potential with respect to standard hydrogen electrode potential. So, that case E is basically nothing but E, because standard hydrogen electrode potential is equal to 0. So, this corresponds to E0. Now, as you go up, this would be E positive compared to this definitely, and this would be E negative. E negative means E minus E0 along from 0 point or E0 point would be negative, and if you compare what is my E positive, this is E negative. E positive means this is minus E0 equal to positive value. So, this is my in the potential axis, and actually when you compare, when you see the actual measurement, that time we polarization by experiment, you will see the potential versus current density. You can also convert into over potential compared to the standard electrode what you have used in your particular experiment. Now, we have seen that this is my over voltage. Now, if you see what is the origin, origin is basically nothing but the thermally activated process. So, now we have seen that if this is my IHP, inner Helmholtz plane, and this is my OHP, outer Helmholtz plane, I have seen that how the my reaction barrier or the activation barrier is changing, and accordingly we have found out this expression. But the point is, if you say this, that means if this process is nothing but the activated, thermally activated jump of those species which are the part of this reaction over an energy barrier or activation barrier, and that is guided by, that is also an exponential function. That means this is a sort of activation controlled. Activation control. So, that means we have to have, for example, if we would like to see what is my cathodic over voltage or what is my anodic over voltage, that time I will just see what is the energy barrier, that is that the ionic species is facing in case of cathodic polarization, or what is the activation barrier the atom is facing to go into ionic spaces during anodic over voltage or anodic polarization. So, it is an activation control, and this is the slowest step in the process, in the overall process. Now, we have to understand why we are saying that this is a slowest step. Slowest step because let us say if you consider the cathodic over voltage, that means you are actually having all the positive charge and they are going and depositing on this IHP. Now, let us say the rate at which this cathodic or the positive charges are getting deposited on the IHP or the inner Helmholtz plane, that rate exceeds the rate at which the further supply of the further the positive charges are being supplied from the bulk solution. Let us understand this more carefully. This is my bulk solution. Let me say this is my bulk. Let us say this is my cathode. This is my cathode. Now you have inner outer Helmholtz plane. This is my outer Helmholtz plane. Schematic, I am just drawing a schematic. Now these positive charges are getting deposited. Now, in order to maintain this positive charge, the depleted positive charge, so once one set of positive charges are getting deposited on this cathode surface, in order to maintain the positive charge ions, the number of positive charge ions on this surface, you have to have a diffusion of that positive charges from the bulk of the solution. So, now for example, during the start of the process, let us say this is my reaction, this is at equilibrium. At equilibrium means the rate at which metal ion is forming and the rate at which metal ion is getting deposited, both are equal. Now suddenly you see that you have some external stimulant or current, or you are supplying extra electron to this system. So you have forward reaction preferentially happening. So you are getting depletion of metal ion. So when T equal to 0, when polarization is 0, so concentration of positive charge, let us say concentration of positive charge something around C0 at this surface. Now when this equal to some, let us say some value, let us say something around some value, let us say this neta C is my over voltage, neta C is over voltage. That case, if I see that C plus equal to C0 again, that means the rate at which metal ion is coming from bulk to this, that rate is more than the rate at which metal ion is getting deposited. So I see that this process is slower than this process, the diffusion process. So that case, my rate controlling step would be the rate at which the metal ion is galloping this activation barrier. So this is activation control. Now there could be another situation. So sorry, before that, since this is activation control, we call it as this, we call it as activation polarization. Now the point is, same situation at time t, this is happening, this is at time t equal to 0. Now the point is, if you see that if the over voltage is neta C and that time C plus at this surface is not C0, rather it is C, and C is less than C0. So I know that initially the overall potential, overall charge concentration is C0, because that time t equal to 0 and over voltage is 0. So C0 throughout the solution we have C0 concentration of metal ion, but once we have started our polarization at some polarization value, I see that C plus concentration at this surface goes to C. So if this surface concentration is C, what does it mean? That means that the rate at which the metal charge is depleting or the depositing is higher than the rate at which this metal ion is coming and diffusing from the bulk to this substrate, to this surface. So bulk concentration is still maintaining C0, but at interface we have the concentration C, and this is less than C0. So, what is the slowest step here? The slowest step here is basically the diffusion of charge, positive charge from the bulk to this interface, rather than the rate at which this activation jump is happening. So, the activation polarization is, the activation jump is faster rate, is happening at a much faster rate than the diffusion. So, I should have something which this polarization has some part which is guided by the diffusion. So, this polarization which is happening because of this diffusion, which is the slowest step here in this case, that time it would be called as concentration polarization. Concentration polarization, why? Because you see that after some time, because of this polarization, I see that there is a depletion of metal charge concentration. So, C is less than C0, and C0 is still the bulk concentration, which is equal to the initial concentration. That means in the start, during the just at the start of polarization, so I see a depletion of metal ion concentration at the interface. So, the rate at which diffusion is happening is slower than the rate at which metal activation jump, ion activation jump is happening from this surface to this surface. So, my activation, the controlling step would be diffusion, and the polarization because of this diffusion is called concentration polarization, and that is happening because of difference in concentration at these two sections. So, you see this polarization which is happening because of concentration difference rather than the actual charge transfer reaction, actual activation jump of this ionic charges from this surface to this surface. Now, if you blow it up there, you will see what are the things that is happening. Let us say this is my metal surface, and these are very closely spaced. So, I can merge these two. So, what would be the concentration when I equal to 0? If I equal to 0, that means the I measured is 0. So, this means IC equal to IA. Now, in that case, what is my polarization? 0. This is my polarization. What would be my concentration at this surface? Concentration of metal ion, that is my C0. Concentration is C0 when I equal to 0 or over voltage is 0. Now, during the course of polarization, I see that the concentration of metal ion just at the vicinity of cathodic surface is going to decrease, because the charge transfer rate from the bulk solution is the slowest step. So, the rate at which the metal ion is depositing there, that is exceeding the rate at which metal ion is supplied from the bulk solution. So, I have a depletion of metal charge at this surface or the metal surface, cathodic surface. So, this is my concentration when I equal to 0, this is when this is my condition or condition case 1. Case 1. Now, my concentration will change to C naught, C, that means after some time when we have gotten some finite polarization. So, case 2 is I have gotten neta equal to neta C, or the over voltage due to cathodic, due to the metal deposition reaction. So, I have dropped this concentration, ionic species concentration has dropped to this. Now, at some larger distance from this metal surface, what would be my concentration? Concentration would still remain this, but you will see and this is a diffusion process, I can have a boundary layer. So, I will see the distribution of metal charge concentration would follow like this. So that means at a wider distance or the bulk of the solution would still have concentration C0, but at the metal surface my concentration of the metal ionic species would drop to C, and this is my boundary layer delta. This is by boundary layer thickness. So this is my boundary layer thickness, which is basically a tangent from this point on this line, on this curved line. Now let me find out what would be the flux of metal charge that is existing there. So I know this equation, m by at equal to I into A by Nf, where I is the current density, A is the atomic weight, m is the mass that is travelling through a section, cross section, A is the area and T is the time. Now from this I can find out that what is my I, N I by Nf. I can see that m by, from this I can find out m by A into small a into T. And what is this? This is nothing but number of moles by area into T. So this is N dash is nothing but the number of mole, total mass that is transferring from one section to another divided by the atomic weight of that metal is giving rise to the number of moles, and you see the number of moles per unit area per unit time is nothing but the flux. So this is J. So I can find out what is my I N F J. Now if we consider that this is a fixed first law, then J is nothing but minus d dc d dx of C. This C is basically the concentration and x is the distance. So this is my x axis and this is my concentration axis, and the concentration is changing this is my x axis and this is my concentration axis, and concentration is changing according to this, and this is my metal surface. So now if we consider that the concentration is varying linearly, so I can see that what is my concentration difference? Concentration is difference is nothing but d C0 minus C by delta, where d is the diffusibility of the metallic ionic species in the solution, C0 is the concentration when there is no current flow, C is the concentration of the ionic species at this surface when there is finite polarization because of current flow. So from that I can write I equal to minus d n f C0 minus C delta, and this is my boundary layer thickness. Now so I know let me so I equal to minus d n f C0 minus C delta. Now when So, C0 minus C I can find out I delta by N F D with a minus sign, and this minus indicates that the concentration is changing from higher to lower concentration. Now, we have two situations, C equal to C0 when this is 0, over voltage is 0 or there is no current flow. Similarly, C would be 0 if we see that whatever charge that is coming from the bulb to this surface is basically going to deposit on this surface by charge transfer, by this equation. So, whatever metal ion is coming from bulk to this interface, those charges will immediately convert to metal atom because of deposition reaction. So, what would be my concentration here? That time C would be 0 and this is I would be 0 in this case, case 1. Case 2, C would be 0 when I would be I max. What does it mean? Current density is very, very large, and the current density you have to find out at some current density you will see that whatever charge is coming, that will have this reaction and that will deposit. So, the concentration at the interface will drop to 0. So, that time I can find out what would be my I. This I would be the maximum because in this case C is going to be 0. So, I can have from these two conditions, I can have some sort of potential conversion. How would I do that? Now, when C equal to C0, I can find out what would be my potential M plus M equal to E0 M plus M. I will just put Nernst equation RT by F. Now, if we consider this is N, this is N. So, this is N, this is N, because if we consider N number of electrons are associated with this deposition reaction. So, that case it would be NF into log of into 2.303 log of C0. Let me write to a little left. C0 means concentration of metal ion. So, I can write Nernst equation according to this formula, and I can put this concentration Mn plus as C0 when I equal to 0. That time the concentration at the interface also would be C0. Now, if I find out what would be my potential if my concentration changes from C0 to C. So, Mn plus M would be equal to E0 Mn plus M plus RT into 2.303 NF log C. So, this is case 1, this is case 2. That means case 1 means when I equal to 0 at this interface my concentration would be C0, and when I has some I value or I max, that time C would be, let us say, some value. In case of this would be C equal to 0, or I can put C equal to 0 when I equal to I, some value. So, this case, let me consider this is third case. So, third case, let me put this is a third case. Third case, I can find out what would be my potential because of this concentration C and when the current is I. From these two equation, I can see that this is 1, this is 3 corresponding to third condition. So, I can see that E m n plus m condition 1 would be greater than E m n plus m condition third, since C0 greater than C. So, what would be my polarization? Because of concentration difference, polarization would be, I can put concentration CONC, because that time polarization would be E final minus E initial. E final is this one, m n plus m third, E m n plus m first. This is my polarization. And you see, we have considered metal ion this reaction. So, it is basically nothing but the cathodic polarization. Okay. Here also this is cathodic polarization, because we see that potential is decreasing since this one is greater than this. And this is happening because of the concentration difference, not because of the metal charge activation jump of the ionic species over the activation barrier from OHP to IHP. Now, from this we can write this should be equal to, these two will get cancelled because these are the standard reduction potential for m plus n to m. These two will get cancelled. So, finally, I would get 0. I will get RT into 2.303 by N F log of C by C0. Now, if it is happening at 25 degrees Celsius, 1 atmosphere pressure, and F equal to 96500 coulomb per gram equivalent, then this value would be 1 by n 0.059. You just put all those values. R is 8.314 into log of C by C0. So, I have gotten one important correlation with the overvoltage, that is because of concentration difference. I will get this. Now, instead of C, I can write the concentration in the form of this. Okay. So, if C equal to 0, that time in this case, if C equal to 0, that time I is basically I max. So, C0 would be equal to minus I max delta N F D. Condition third. Condition second. This is related to condition second. Similarly, I can write what is C. C would be equal to minus I delta N F D. Sorry, C0 minus C equal to, this is condition this. So, I can replace this I and I0. So, let me replace I and I0 equal to 0.059 n log of, you just replace this, you will get 1 minus I by I max. So, this is a very, very crucial expression, and this expression tells you what would be my polarization because of concentration difference. So, this is nothing but the concentration over voltage.